Well, welcome everybody. Second Tuesday of the month. Every month we will have these parties here in Peyton Hall. And I'm the assistant director of the AAAP. Rex, who's on Zoom, is the director, and he'll be leading a lot of the uh, evening's stuff. But I'm going to start by just introducing you all, saying hello. And and I don't think I have any other special things to say. We're going to have a speaker who's uh, just had to switch computers, so she'll be back online in just a minute. And Victor here will introduce her. We can wait a minute until she comes back before you introduce her. Um, and then she'll speak for about an hour-ish, and then we'll have a Q&A, and then we'll take a little bit of a break, and then we'll have this thing called the Unjournal Club. Did I do that in the right order, Victor?
That's right.
Okay. uh, and we'll have two speakers in the Unjournal presentations today. One of them is the director, and the other one's the assistant director. Rex first and me second. Anybody else wants to talk, you're welcome to. And we'll probably spend a little bit of time, I'm not sure if this is true, we'll probably spend a little bit of time showing pictures that we took last night. Some of us took last night of the big event where the moon passed in front of that planet, which is called Mars. And so that was quite fun.
So let's talk a little bit about what Rebecca is going to talk about tonight. Her talk is entitled Our Moon Ourselves. The moon is one of Earth's most unique features, and the two comprise what has often been termed a double planet. This unique pairing shapes all of the other things that make our planet special, from its geology to its multitudes of life, including us. Life might not have evolved on Earth at all without the moon's stabilizing gravitational influence and powerful tides. After we humans showed up, the moon quickly became our primary way of telling time and organizing our lives. It shaped our understanding of our place in the universe and helped us to invent forms of religious devotion and the process of science. The moon plays a central role in our most famous wars, our greatest adventures, and our shared futures. And now humans are trying to go back to the moon's surface soon, hopefully, and with plans to stay. We owe ourselves a thoughtful consideration of the moon's role in our history and our future. And a few words about our guest speaker, Rebecca Boyle. She's a science journalist. She's reported from particle accelerators, genetic sequencing labs, caves, bat caves, the middle of a lake, tops of mountains, and the retractable domes of some of Earth's largest telescopes. This is her first book, Our Moon, How Earth's Celestial Companion Transformed the Planet, Guided Evolution, and Made Us Who We Are. It's a new history of humanity's relationship with the moon, which Rebecca looks forward to visiting on assignment. Our Moon is a national bestseller and was longlisted for the National Book Award, is a New York Times Book Review Editor's Choice, and is one of the New Yorker's best books of 2024. Based in Colorado Springs, Rebecca is a contributing editor at Scientific American, a contributing writer at Quanta magazine, and a columnist at Atlas Obscura. She's a frequent contributor to the New York Times, The Atlantic, and many other publications. So without further ado, I welcome our guest speaker, Rebecca Boyle.
Thanks, everybody. I just want to make sure I wasn't muted. Thanks, everybody. Thanks for having me. And I'm glad to hear that maybe a couple of you have maybe read the book or have heard of it, at least. That's always a good sign. Yeah, it's been a kind of a crazy year. It will be actually a year ago, well, technically today, because books always come out on Tuesdays in this country. If you ever noticed, a new book's publication date is always on a Tuesday. In the United Kingdom, it's always on a Thursday. So it was January 16th of last year, which was a Tuesday. And so the actual anniversary is Thursday of this week because of leap year, but today is the 1 year anniversary. So it has been a very big year in a lot of ways. And I think when I talk about this book, one thing I mention is that I think there's a reason why I feel like people have responded to this book, I hope in a positive way. And it's for a few reasons, but really it's because the moon is such a huge part of all of our lives. Everybody has a story from when you were a kid, or your children or your grandchildren or friends, about being outside under a full moon, or like looking at it through a telescope for the first time, or some of these sort of formative experiences that I'm assuming a lot of you in an astronomy group have had under the night sky. And, at the same time, there's a lot going on right now on the moon. There's tomorrow a launch window opens for SpaceX to send 2 lunar landers that are sharing a rocket. One is from a Japanese company called iSpace, which launched last year as well and kind of tipped over, but it landed. And another one is a private company funded through a NASA grants under the Commercial Lunar Payload Services program. And they both have contracted with SpaceX to fly, and SpaceX is being efficient and sending them both at the same time. And that window opens tomorrow. So like quite literally here in the next week to 2 weeks, depending on their trajectories toward the moon, we'll have, yet another new generation of landers. This time, again, for the first time last year, and now for the second time in history, these are not NASA-sponsored, government-contracted, taxpayer-built spacecraft. These are privately funded with some public funding in some cases as well, but it's not like the old days of Apollo, where you have contracts for, large heritage companies building huge rockets and huge ships to get to the moon. These are now commercial ventures funded by private capital, private equity, and in some cases by government as well, to try to create a new path to the moon. And it's, I think, a really important kind of touchstone for our culture. This is something that is exciting in a lot of ways. I want to go back to the moon. I think we should go back and we should be getting more samples. We just got some fresh samples from another Chinese lander. And it would be great to get more from American funded rockets, but at the same time, anything that happens to the moon right now is going to happen to it forever. And I think we sometimes can lose sight of how fundamental that is, how transformative our experience on the moon is going to be for the moon, and let alone for us. It's exciting for us. It's great to inspire younger people to study rocketry and space and astronomy and physics, but the moon doesn't have these processes that Earth has where it can erase its past and remake itself. And so that's a big responsibility, I think, on all of us to at least be thoughtful about what we're doing up there and why we're doing it and who we're doing it for and who we're doing it with or against. And that's very much in the news right now. And that really is kind of the upshot of my book is, what do we owe the moon at this point after all this history and, human philosophy and religion and modern science and all these projects that we've undertaken, that the moon has, I argue, shepherded or enabled in some ways. Now what are we going to do? So that's kind of the overall message, I guess. And so with that, I guess I will kind of go through what the book is about. And I will say that one reason I wrote this book is because I'm an amateur astronomer myself, and I also write about astronomy professionally, for magazines. And I talk to a lot of astronomers, and a lot of times they're like, and you probably appreciate this, that like the moon is so bright, like it's really annoying, it's in my way, I need to like plan my observations around it. And now it's full, yeah, sure, great, there was a Mars occultation last night, that was cool, but I want to look at some deep sky objects, and I can't do that when there's a full moon. So it's a sort of like annoying thing. And that's true of professional astronomers too. If you're working with the Very Large Telescope in the Atacama Desert in Chile, you need to wait until the moon is setting over the Andes to take your observations, because otherwise it washes out your image. It's the telescopes are so sensitive that you cannot use your car's headlights when you leave these observatories, which I once had to do when I visited the VLT in Paranal. I was there for sunset, and they opened the dome and they kind of turn everything on, and they're getting the optics going. And then it was time for me to leave. And the observatory director was like, "Oh, yeah, by the way, you can't have on your car lights. There's no lights. So good luck." And so I drove down a mountain in Chile in the dark. And there was a moon that night, luckily. It was a first quarter, so there was enough brightness for me to see the road mostly. But that's how sensitive these things are. So the moon is really in the way. And this book came about in part because I was like, well, but the moon is cool. Like, we should still care about it and talk about it. And this book started as sort of my appreciation of what the moon is and what it's done for us. And the more I researched it, and I spent 5 years working on this book before it came out. And the more I dug into all these subjects, the more I sort of came to believe that the moon really is responsible for so many of these giant leaps that we've made as a species, from the evolution of life to the stability of Earth's climate to the invention of religion and philosophy and science. And that's what the book sort of turned into, is this more like an argument for what the moon represents to us and what we should then at least consider what we owe to it, given all of this history. So I don't normally have slides because I'm just not a slide person, but I do have some. So let me make sure I can share, because sometimes Zoom doesn't like when I share my screen. Let's see here. Hold on, sorry. Can everybody see?
Yes, we
my
can.
screen? Okay. Okay. Okay, Zoom. Okay, I will just play. Okay. Oh, now I see everybody over here. How do I? Okay. Sorry. I don't do a lot of slide presentations. Okay, there we go. Okay. So this is my book. And the subtitle is very wordy in the US. It's How Earth's Celestial Companion Transformed the Planet, Guided Evolution, and Made Us Who We Are, which is quite literal in terms of what the book is about. And the UK version is a little bit more poetic, and it's just a human history, which is really what the book is about. Oh, this is just some information about it. This is to prove to all of you that it was worth reading. The biggest surprise was the National Book Awards thing, which I still don't understand how that possibly happened, but that was very awesome. And I got to go to Miami for this big Miami Book Fair, which was a kind of culmination of the year for the book. So it's been really gratifying to see people respond well to it. So I'm going to jump into where I start the book, which is a story that some of you know, or maybe know very intimately, which is a couple of seminal battles in World War II. The most important one to me and in the book is the Battle of Tarawa. And that's here on the left. This is the coral atoll of Tarawa, which is now part of the nation of Kiribati. These are sort of iconic D-Day images from the invasion of the beaches of Normandy. The moon plays a vital role in both of these battles in ways that we took until the 2010s to really fully understand. And I'm talking about in terms of the actual like orbital physics of what was happening at the time. So in November of 1943, we are at war on two fronts. We are, fighting in the Pacific theater against the Empire of Japan. And there is this multi-part plan among the Allies to get closer to Japan via this chain of islands called then the Gilbert Islands. And it's kind of this multi-part. We have to get this island, then we can get that airstrip, then we can reach this island, and then we can get that airstrip, and then we can frog hop through the Pacific closer to an eventual invasion of mainland Japan. And a key battle in this plan is the Battle of Tarawa. So on November 20th, 1943, the Allies decide to try to take this island. And they know they have to plan for a high tide, because as you can tell, this is a very thin piece of land. This is barely, it's not even really quite an island, it's an atoll. It's built by coral over time. And there's an enormous barrier reef in front here. And this is the land. This is all Tarawa is. There's an airstrip, which the Allies really want to be able to access the next chain of islands. They know they need to get a high tide to bring water up at least 5 feet over the coral reef to float their flat-bottomed Higgins boats to get closer to the actual land. And they plan the invasion the morning of the last quarter moon rising high tide. And the tide does not come. Somehow, nobody figured out why until 2010, that it was called the dodging tide. The tide does not come in over the reef. The boats get stuck, and the Marines in this battle have to get out of the boats and wade across, 500 yards to shore, holding their rifles over their heads while Japanese soldiers are shooting them. So it ends in the worst casualties in the history of the Marine Corps to this day. And over 2 days of fighting, 3,000 men are wounded, 1,100 are killed. And that's just on the US side. And eventually we do take the island and overcome this gravely terrible battle to eventually move on to further islands in the Pacific. And I learned about this story as a kid because my grandfather was there and survived. He was a bomb, I don't remember the actual Marine technical title of his job, but his job was to install the bombs on the planes that prepared for the ground assault. So he was on Nanomea Island, which was a couple 100 miles south, the morning of this battle, loading all the bombers with ordnance, which is then dropped on the island to prepare for this invasion. And a couple of days after the battle is over, he arrived on Tarawa itself, after the Seabees have kind of cleaned up, and the same thing happened again. He started loading planes that were taking off from Tarawa's airstrip, which you can kind of see over here, marching on to another chain of islands closer to Japan. And I knew as a kid, this was like the worst battle in the history of the Marines. It was this legendary story in my family. And I didn't know until working on this book that the reason why it was such a bad situation was because we misjudged the moon. The tide didn't rise because no one knew, it was impossible to know before its satellite era, what would happen as the tide met the geography of Tarawa, because it was a neap tide. It was high tide during a period when the moon is furthest in its orbit. So this is the opposite of a supermoon. It is as far as it gets in the year. There were only 2 apogee and neap tides in that entire year, and one fell on November 20th of 1943. And it took until 2010 for an astronomer at the University of Texas to figure out this alignment, going back through ephemerides through NASA and tide charts to figure out why this tide failed the Marines. And I was kind of blown away by this. And this is where I start the book, in part because it's my own family's history, but in part because I think it's just a great illustration of how we take the moon for granted in ways that we don't even think about. They knew we needed the tide, and the moon is, the reason we have a high tide. That was kind of vaguely known. We all know that. And it was like, oh, we got to judge the high tide. But there are all these other interesting interplays between the Earth and the moon and their gravity and the gravity of the sun and the orbital dynamics of these bodies. And nobody really fully appreciated that relationship in 1943. And we learned enough about this, that this happened, that this created the Office of Naval Research, which exists to this day to understand the oceans better and understand bathymetry and how coastlines work with the tide to shape the way that currents flow and the way tides rise for national security purposes, but also to understand our planet better. But in the few months after this happened, is the invasion planning for D-Day, for the invasion of France, to liberate France. And Hitler, was aware of efforts by the Allies to make it onto mainland France, but the French resistance was pretty good about using full moons actually to smuggle information by moonlight, bicycling through towns, to cut phone lines and things like that. And Churchill writes in his diary about how we needed full moons to invade. We needed the light of the full moon, and we needed a high tide. And so the most auspicious day was the full strawberry moon of June 6th, 1944, which, so the moon is full overnight and setting at sunrise. And it would be bringing in a high tide that morning. So the Allies planned the invasion so that the paratroopers from the 101st Airborne can float over the English Channel without instruments and without any light at all, just the moon, to illuminate the bridges they had to take to capture this part of the coast of France. So within the span of 6 months, between the invasion of Tarawa and the invasion of France, the Allies learned how much we needed to rely on the moon. And I tell that story because I think it's just an interesting example of how we don't think about the role that astronomy plays, even in things like World War II, where we all know these stories. We grow up hearing them, and we watch movies about them, and we read books and nonfiction and fiction about them. It's just such a, cultural touchstone in the 20th century that everyone knows the stories, but you probably didn't know the stories about the moon. So after this, I divide the book and my talks about this kind of in 3 different parts, because I feel like first we need to get to know the moon. Like, we need to understand what it is and why it's here and what it's doing, and how it shapes this planet. So, I think the most intriguing thing I learned in this sort of section of research is that we don't really know why the moon is here. Like, it's weird. It is huge relative to Earth. The only thing that even comes close in our solar system is the Pluto and Charon system, which isn't really even technically a planet. Like, it's sort of a weird kind of binary world, where Charon is 50% the size of Pluto. Pluto's not even really considered a planet anymore. It's a dwarf planet. So there's really no comparison to Earth and our moon in this solar system or in any other that we've ever found. There are people looking for exomoons around exoplanets orbiting other stars, but so far no one has found any convincing evidence of these moons. So our moon is really unique. Its formation story is also unique, and I think really has a lot to say about how lucky we are on Earth to have this thing. So what we think we know is that sometime when Earth was very new, only a couple 100 million years old at most, something the size of Mars slammed into Earth and obliterated it and obliterated itself. And both of these worlds were so totally destroyed that they both kind of consumed each other and recombined to create the Earth and moon system that we have. This is a story that we learned from Apollo by looking at the rocks that the astronauts brought home. The way that the places they were found and the composition of these rocks suggested that the moon had to have been at one point totally molten. And these rocks formed as sort of like a crust, like, a day-old pudding cup, gets this kind of film on top of it. And that's the bulk of the Apollo samples, especially for the first couple of missions. And this told this kind of narrative that, like, something really horrible must have happened early on for the whole moon to melt and for these rocks to float through this molten global lunar magma ocean, and to cool and solidify on the surface for us to bring them home. And that led to this theory that there was some kind of giant impact early in Earth's history. And for a while, we thought that was it. It was that simple, that, and for a while, meaning like 50 years, not a very long time in the scope of human history, but a long time in terms of modern science. And only in the last maybe 10 years have planetary scientists started to sort of poke holes in that theory. It's probably still what happened, generally speaking, like, because of the way the moon is, where it is, how large it is, how fast it's spinning, how fast Earth is spinning, how distant it is from us now, which is actually quite far. All of these things kind of have something to say about what must have taken place in the past. These are your parameters that you plug into your models. And so we know this probably happened, but we don't know how or why and what all, came down after that. And in the last few years, there's been a really interesting efforts among both supercomputer, astronomers trying to figure out the physics of this process, and in just geophysicists and geologists looking at the rocks and trying to piece together like what these are made of and what Earth rocks are made of. And, it turns out that the Earth rocks and the moon rocks are basically the same. There is almost no distinguishing trait that you can use to separate them. If you have a bunch of rocks and you pick one out and look at it, and looking at it being a relative term for things like, isotope geochemistry and mass spectrometry and these other kinds of methods, you can't tell which is which. And that's weird for a lot of reasons. We know a rock from Mars is from Mars. We know we have Martian meteorites that have landed in Antarctica and been picked up by scientists, and we can tell them apart very easily from Earth rocks simply by looking at their chemistry. The ratio of oxygen, for instance, in the Mars rock is very different from ratios of oxygen isotopes in Earth rocks. Initially, we thought that was the case for moon rocks and Earth rocks too, but with better methods in the early 2000s, especially now, and after these new Apollo next generation sample analysis programs that have been happening in the last couple of years, we have taken a much closer look at the different isotopes of things like argon and, again, oxygen, tungsten, hafnium, all these sort of relationships between isotopes, and have been unable to really make a distinguishing argument between Earth and moon rocks. They're pretty much the same, which doesn't make a lot of sense in terms of planetary science theories. We know when planets are formed around the sun and other stars, they condense their chemistry at certain temperatures and pressures around the young sun or the young star. And there's kind of some rules of chemistry that the way that these things condense out and solidify. And so it's almost like a fingerprint. This is why we can tell a Mars rock from an Earth rock, because we know where Mars formed. We know where Mars is now. We know where Earth formed and where it is now based on orbital dynamics. And we can do some sort of chemical sleuthing to tell these places apart. And so if that's the case, this thing that hit Earth, which we call Theia, was the mother of the moon in Greek mythology. If Theia hit Earth, then the moon would look like Theia, but the moon looks like Earth. So somehow they mixed completely and both kind of recoalesce into these separate worlds. And that's where this really interesting and controversial planetary science is happening right now. This is actually a super heated debate in the halls of planetary science conferences. And right this week at AAAS is happening in Maryland. And it's interesting because we don't really know how the moon came to be the way that it is, where it is, the size that it is. And we'd like to know that story because it's just important to know our past, I think, but also because it sort of sets the stage for the Earth that we have now. And that includes the climate of our planet over millennia, the axial tilt of our planet, and the reason we have seasons. We're now at, a few weeks past the solstice. And so finally getting a little longer days and maybe a little warmer, not quite here yet for me in the mountains of Colorado, but at some point it will get warm again because Earth's axis is tilted at 23.5 degrees, which we all know. That's not the case for other planets. Their axes are tilted at varying degrees over tens of millennia or tens of millions of years. Earth stays pretty stable over time because of the moon's gravity. So the moon keeps Earth from wobbling like a top, the way Mars does, the way that, Venus is a whole other story. Venus kind of goes backwards, so that's a whole other thing. But other planets have much more, what's the word I'm looking for? Much more variable axial tilts especially over evolutionary time. Ours is pretty stable, which is nice. If we didn't have the moon, depending on whose research you believe or look at, Earth's axial tilt would go between 23.5 to 90 degrees or 45 degrees. There are these really extreme shifts in the direction of its magnetic north over millions of years, tens of millions of years, which doesn't sound like a long time, but in terms of the evolution of life and complex life especially, is a lot, going to do a lot. It's going to mess you up. It would make it a lot harder for life to have taken hold and held on. Imagine, the equator kind of, or doing what Uranus does and kind of flipping on its side, and the equator is now pointed at the celestial north and never seeing the sun, and the poles of Earth are where the equator is now. So all that ice is going to sublime and melt, and that's going to do a lot of bad things to the atmosphere and the overall climate and the water cycle. And we know this is true because this is what happens on Mars. Over time, the Martian polar caps sublime and a bunch of carbon dioxide is injected into the Martian atmosphere, and that can really change what Mars looks like. So we should be thankful that the moon does not do that, because that keeps it a little bit more stable here over time. And its history, its evolutionary history, its geologic history, I should say, is one reason why that story is the way it is. So we talked about the origin of the moon. This is why I don't use slides, because then I get ahead of myself and I forget what I'm talking about. So this is one of the theories for one of the newer theories I happen to think is very compelling about the way the moon formed, is this sort of new planetary structure called a synestia. And that's what this might have looked like, where it's this sort of bagel-shaped, cloud of hellfire, in which this core here becomes Earth, and this other object becomes the moon. And this is how they might have formed in this vaporized kind of bagel of gas. And the seasons, we talked about that, why Earth is nice. And eventually, why that stable climate and seasonal cycles end in us. So this is the part of the book where I was very surprised by my own research, and I kind of wanted to go back and figure out what is the earliest thing I can find, or what is the earliest thing I can attribute to the presence of the moon, or the formation of the moon, or the tide, the influence of the moon today, the gravitational influence of the moon. And I was just trying to be pretty agnostic about these things, and assume that if the moon plays a big role in stabilizing the tilt of Earth's axis over time, and maybe keeping Earth in the Goldilocks state where it's just right for liquid water, not too hot, not too cold, that that would have probably also played a role in the evolution of life. And it turns out that it did. And I think, as I argue in the book, it may be one of the most important factors in the evolution of life, especially complex life on land. So imagine if we didn't have the moon, the ocean is this sort of still basin. There's still some tidal influence of the sun. There's still some tidal flexing of the oceans based on the gravity of the sun, and maybe Jupiter plays a little bit more of a role. So there's still some movement of water, but it's nowhere near the way that it is today, especially nowhere near the way that it would have been 4 billion years ago, 3 billion years ago, when we think life first took hold. The moon was much closer, so the influence of its gravity over Earth was much stronger. So the tide would have been much more extreme. So you can imagine stirring the entire ocean like you're stirring a pot of soup, and the stuff from the onions in the bottom and the sludge from your, browning your onions kind of mixes up and goes within and makes the soup interesting. And the ocean is doing the same thing with the influence of the moon, stirring up nutrients from the seafloor that otherwise would have just remained there. So if life originated in the deep ocean, which is sort of the more, I don't want to say trendy, but it is a little bit trendy, but the more recent argument in evolutionary biology circles is that the first life on Earth came from deep ocean vents. That's where it first flourished. Because there's this interesting hydration and vaporization cycle, and there's lots of interesting minerals coming out of basically leaking out of Earth's mantle to superheat the water. And if that's the case, then the moon probably is what dredged them up and maybe helped them encounter the sun for the first time and photosynthesize for the first time. If it didn't exist, that might not have happened. We don't know, obviously, but I think this is a pretty compelling theory. And then what we do know is that after life evolved here, after the first couple of boring, billion or so years, all of a sudden we reach an age about 350 million years ago when the oceans are teeming with complex life, including two main groups of fish. One, the lobe-finned fish, that are these kind of big shouldered, kind of lumbering things that are big, fleshy fins. And then ray-finned fish, which are these little things that we still catch and eat today in the form of salmon and your goldfish, and the aquarium I have upstairs are these ray-finned fishes. And the differentiation between these two types of fish happens in the Devonian period, 350 million years ago or so. And this is also the period where life first comes onto land, backboned life, I should say. Invertebrates have done it already, and plants have begun to do it as well. The Devonian is the age of fishes, but also the age of trees. So this is when we know through the fossil record that the first fish come onto land and then eventually breathe the air and evolve into dogs and elephants and us and everything else that has a backbone. And whales, they go back into the water later. And it turns out that this was such recent research, this almost didn't make it into my book. It was like during the fact checking process that I was like furiously typing with these researchers to get this into the book, that there was a series of studies in 2020 looking at ancient bathymetry, so trying to reconstruct ancient coastlines based on ancient seafloor and geological, like the records of continental plates from the ancient past, combining that with physical models of the distance between the Earth and the Moon and their mutual orbits and gravity, and the paleontology record, where fish fossils are found and which land masses on Earth today. And it put together this really compelling picture that the Moon is what dragged them out of the water and put them on land and left them there. And the strongest of those are the ones that learn to breathe air instead of exchanging water through their gills, and the ones that learn to use those fleshy front fins to move themselves across the sand instead of through the water. And that's how we all got here. And there's, a couple other arguments about whether that's true. Some evolutionary biologists think that it was more about the proliferation of plants on land. Fish were trying to come onto land to eat those plants. But it seems very likely, at least to me, that the Moon played a very large evolutionary pressure in bringing vertebrates onto shore, which I don't think has been really well appreciated in paleontology circles until very, very recently. Which again, I think is just super compelling. We don't think about the Moon when we think about things like the evolution of, tetrapods and dinosaurs and non-avians and all these things. But the Moon probably played a really important role in all of those things. And so then eventually these fish come out of the water and invent philosophy. Okay, this is, again, getting ahead of my slides because I don't need slides. This is a fossil that is probably the most important tetrapod fossil ever found. This is Tiktaalik, and this is a rendering of what it might have looked like. So this is our great times, log something grandmother. And these fish are really interesting in a few ways. They have a large jaw. They have these really tough kind of shoulder muscles and then wrists. They have a lot of the same bones that are in your arm today, an ulna and a humerus and your scapula. A lot of these bones are found in these fish for the first time in this era when the Moon is closer to Earth, exerting a extreme force over these tidal basins, which I didn't mention, which this is an important piece of the puzzle. This is when Pangaea is starting to form. So this is the famous dinosaur supercontinent that gives rise to the dinosaurs. This land mass of Earth, all kind of mushed into one, is beginning to form in this era. So ocean basins are closing. So tides are very extreme. So there's a tidal resonance in some areas, which means that the water is moving in or out at the same rate that the Moon is orbiting Earth, essentially. And there's this, syncopation of the water to the geography of the land. And you can get this extreme change in the height of water in a couple of hours, like 80 feet of water from high to low tide in the span of just a few hours. So if you're a fish in the shallows, like you better get out of there, fast, or you better learn how to breathe air and move across the land because you've been stranded. And it seems pretty compelling that that's what happened. And that's what we would have looked like back then. So after these fish come out of the water and invent philosophy, humans first start to take note of the cycles of nature and use them for our benefit. For the first time, we think, least as old as can be documented, is the Paleolithic period. So this is like, 30,000 something years ago, when humans were living in caves in Europe and elsewhere, but this is where the oldest artifacts of human culture, if you want to call it that yet, are found. People figure out that you can divide up nature, you can divide up seasons, and you can begin to take command of those things through this division. And the first division of these things is our division of time using the moon. There's a reason why we call it a month, and there are 12 of them. This dates, back before people can keep track. And every culture on Earth, on every continent on Earth, did the same thing, found ways to mark time using moons. From one moon to the next would be 1 month, or whatever division you want to call it. And you can break that up into smaller pieces and call the half moon cycle something else, call the first new moon cycle something, call the full moon something. The Ides of March is one example of how people use different names and phrases for the phases of the moon as it changes throughout the month. But there's a problem if you're doing this to divide time, which is very easy to do because there are 12 moons in a year, and you can figure out when the moon is half full, I will meet you at this tree and you owe me money, or whatever your needs are. You can use it in a very convenient way to break up the time that has passed or the time that is to come, which is even more important. But this doesn't quite align with the sun. The solar year is 11 and a half-ish days longer than a lunar year. So after a couple of years, if all you use are moons to count time, you're out of sync with the sun. So almost every ancient calendar figured out ways to combine these two things and use the moons to break up the year into 12 months, 12 segments, for 12 full moons and the time it takes the sun to return to the same solstice. But you also have to count for this extra time. So people figured out ways to add months, or now we use leap days, or we use intercalary periods. The Chinese calendar is about to have its new year in about 10 days. Well, 2 weeks. It's the 29th is Lunar New Year. And the Chinese calendar uses this complicated series of 19 years, which relates to the moon's, it's very complicated, like phase of lunar stices instead of solstices, lunastices, which we call lunar standstills, which we're in one right now. Every 19 years or so, the Chinese calendar adds 7 years to like reset the calendar. And I don't really understand it, nor do I understand the Mayan calendar, which also is a very sophisticated system of like interlocking calendars that realign the lunar year with the solar year in ways that you can use to keep track of time that is correct seasonally, but uses the moon as your primary timepiece. So people figured out in the Paleolithic how to do this for the first time. They figure out that there are cycles in nature that we can keep track of to note time that has passed, which I think is what this artifact represents, and to note time that is to come, which we'll get to. So this is one of the most famous artifacts from the Paleolithic. This is the Blanchard bone shard, found in a cave in France by a journalist like me, by the name of Alexander Marshak, who wrote during the Apollo era. He was under contract to write a book about why humans wanted to go to the moon. Why was this such a compelling project for the human species to get there, walk around, hit golf balls, and come home? And he was trying to interrogate the relationship that we've had with the moon. So very similar to what I set out to do in this book. So he was kind of a godfather to me in my thought process. And at one point, he is overwhelmed with the sheer time that he has to go through of human history to make sense of this project. And he just opens a random drawer. This is the story he tells in his book, which is The Roots of Civilization, pulls out this piece of bone. And there are countless things like this in drawers throughout France and Germany in these museums of ancient history. And people for a while looked at these things and assumed this was like tool making. Oh, they're just going to sharpen their spear tip. And that's why these are like random marks, you know. But Marshak is one of the first people to see a pattern here and he sees this looping pattern of comma shapes that get bigger, and then they're circular, and then they get smaller, and then they get bigger, and then kind of loop around in this serpentine pattern. And he sees this as this. He sees this shape as a cycle of moon phases. And so Marshak believes this is one of the earliest known lunar notation tool, that people were using this as a type of calendar system to keep track of time as it goes by, which was a huge change from what people thought humans in this period of time were capable of. And his work is still controversial. And, you know, not all anthropologists think that this is right at all. Some people think it's ridiculous, but some people think he was spot on. And I guess it depends on which anthropology department you talk to. I'm not sure what Princeton says about this, but I personally find this super compelling. And it makes a certain kind of sense to me that if you're living in literally the Stone Age, you know, 30,000 years ago, before written record that survives to today, that you would have needed some way to keep track of the time that has passed, because you need to know when to plan for something that's to come. And that brings me to this expedition that I went on in northeastern Scotland. This picture is of the Tomnavary Stone Circle in Aberdeen, which is one of the oldest lunar monuments on Earth. There are these series of megaliths throughout Northern Europe. You probably all know of Stonehenge. That's the most famous one, but it's not the oldest. And it's, you know, I don't think the most interesting in many ways, although we do think Stonehenge probably had a lot to do with the moon as well as the sun. Tomnavary is interesting for a few reasons, but one is that it is thought to be aligned to this, I don't know how much I want to get into the metonic cycle versus these other cycles, but there's this, the lunistus, the lunar standstill cycle, is this important 18.5-year cycle where the moon goes to these very extreme positions in the sky. And those of you who are sky watchers probably have noticed this or know about this, and I'm preaching to the choir, but we are in the major lunar standstill right now, which is a way of describing how the moon seems to, you know, rise and set at more extreme latitudes in the sky throughout this period of time, and then return and go back the other way, the same way the sun does during the solstices. So winter solstice, the sun in the northern hemisphere is at its southernmost point. It seems to stand still for a day, a couple of hours before seeming to move back the other direction, which just has to do with Earth's orbit around the sun. But the moon does the same thing. And we're in the height of that cycle right now. This full moon last night is the highest full moon, highest meaning like the most extreme, you know, overhead angle that the moon will reach for the next 18 years. And where I live in Colorado, this is a very important time setting event for the ancient people who lived here before me. The ancestral Puebloans knew of this and used it, just as the people who lived, the Celts who lived here in Tomnavary in northern Scotland. And this would have been a time where they would do some probably levels of ceremony. There would have been very important gatherings that were happening around this time. And it would have been a really important time to reset their calendar and to do whatever sort of process they had devised, which again, as the ancient Chinese calendar did, other calendars on Earth, to align the sun and the moon in a way that allowed humans to more carefully track time. Northeastern Scotland is also interesting because, I guess I didn't get into that one yet, but it is the first time, the first place where humans arguably learned to predict future time. And in addition to Tomnavary and other stone circles I visited, there's this field dug into the side of this field next to a 15th century castle built by Robert the Bruce, where there are a series of curved pits kind of dug into the ground. They start out small, they gradually get larger. The center one is the largest, and they gradually get smaller again. And there are 13 of them. And this alignment of dug out pits dates to 8,000 BC. So 10,000 years ago, when hunter-gatherers would have been, you know, chasing salmon up the river in that part of Scotland. And this is thought to be the oldest calendar on Earth, the oldest megalith or the oldest alignment of any kind we've found so far that suggests this relationship between people and the sky, and how we were not only using it to track time, past time, like Marshak had seen, but to predict future time, and to use the moon to do that, to say, like, in the fifth moon of the year, I need to go north to find the salmon, or I need to go to this place to find this game, and allow people to move mentally in time, which is a huge cognitive leap. As far as we know, we're the only species that does that. At some point, we can use AI to ask the whales or elephants if they do the same. But as far as anybody knows, humans are the only animals that can mentally time travel. And I think astronomy is the reason why that is possible, our understanding of astronomy. So this gets more complicated as people get more complicated, as people get more sophisticated, and language gets more sophisticated, and we start inventing language, and we start inventing the written word. This happens in the Bronze Age in Mesopotamia. And in Europe, there's no record of a written language that survives to this day, but maybe there was. And people were very sophisticated sky watchers at this point. They were able to figure out how to align the lunar and solar years in a way that was like a form of math, and were much more sophisticated about these things than people ever gave them credit for. One of my favorite artifacts in this book, and my favorite stories in this book, is the story of this thing, the Nebra sky disk. It's the size of like a dinner plate, maybe. And it's this beautiful copper and gold disc. This is verdigris. This is this like furred, kind of copper, furry green patina. But this is gold. This is either the sun or a full moon. This is the Pleiades up here. This arc at the bottom is a solar bark, which is like a solar boat, which is a legend in lots of Nordic and Scandinavian legends that the sun uses this boat to traverse the sky during the solstices. And this arc here is matched by one here that fell off in antiquity, and is supposed to represent the angle at which the sun rises and sets at the two solstices in this part of northern Germany where this artifact was found. And this is obviously the moon. Anytime you see this shape, you know what it is. There's no other object on this planet that is represented by this shape. And so this is thought to be a calendar device, a functional device, in addition to being really beautiful and interesting. This dates to 3600 BC, and shows this great level of sophistication. Like the tin is from Cornwall, which means they had these great trade networks to reach that far north. And some of the gold is from the Carpathian Basin. The people who made this had to go pretty far to get the materials to make this thing. And it's interpreted as a time setting device. When the moon, a new moon of a couple of days, this shape, is near the Pleiades in the spring, this is time to reset your calendar. This only happens about every 4 years. So some shaman or some astronomer in 1600 CE figured all of this out and created this object to use this thing to be able to orient ourselves in time. And I find that just extraordinary. And then a little further east is the Fertile Crescent and the Mesopotamian cultures, where people invent writing for the first time, people invent religion for the first time. The moon plays a major role in all of this as well. And I think is the starring character of the stories that make up the versions that we know from the Bible of, the people who lived in this place at this time. This is King Nabonidus, the last king of Babylon. And those of you who went to Sunday school or Hebrew school have maybe heard the story from the book of Daniel of the writing on the wall, Belshazzar's feast, some of these iconic stories from the Old Testament, the Hebrew Bible. The king in those stories is misnamed. He's called Nebuchadnezzar, but that was actually somebody else. But it's actually this guy. The stories are about him, Nabonidus. He is the last ruler of Babylon in one of the most glorious cultures in the history of Earth. He restored this ziggurat. This is the ziggurat of Ur in near what's now Nasiriyah, Iraq. And he was an archaeologist. He was very devoted to the moon at a time where his culture, his country, had moved away from the moon god as the primary deity and revered the sun god Marduk, who was the sort of head of the harvest and most important god in the pantheon at the time in the Neo-Babylonian era. But Nabonidus would not give up on the moon. He ends up leaving for a while, goes on a walkabout to restore other temples to the moon in honor of his favorite god. And the book of Daniel's story and books from contemporary Greek historians at the time talking about the fall of Babylon explain how he left the city in control of his son Belshazzar, who is then drunk at a feast, and the marauding army of Cyrus the Great comes in through the city walls and takes over, and the Jews are freed. And that's the context in which most people hear this story. But I think it's interesting because it is sort of the first fall of the most important deity until the Abrahamic deity, which was the god of the moon. The god of the moon is the first and most important god in most of the cultures up until that time that are in Mesopotamia. So he features in the very beginnings of the Sumerian culture. This is like 2,000 years before the fall of Babylon. He's a very important god, and he's right here first next to the king who's holding his royal staff to show the primacy of the moon god to this guy. And his inability to protect his people, his most ardent supporter, the king, is sort of the first time that the moon god falls from grace. The first fall of the moon in my book is this story of how Babylon, the city of Babylon, falls to the Persian Empire. This is a whole chapter that I am very obsessed with, but I won't get into much more for a group of astronomers because it's not necessarily what the book is about. But I think it's very interesting about just how important the moon was to the earliest thinkers, the earliest written language, the earliest philosophers, the earliest devotees, the earliest poets write odes and hymns to the moon. It's the most important feature in the oldest cultures on Earth. And I think that's, has something to say to all of us. So after the Greeks, the Persians take over, Alexander the Great and his friends sort of take over the Mesopotamian world, they invent philosophy. So I have a few of the famous starring characters here. It's Plato, this is Anaxagoras, this is the Ptolemaic system, and this is the School of Athens. This is Raphael's painting of the School of Athens in the Vatican. I think there's this interesting transition, again, going back to like looking for the oldest example of something I can find, or the oldest, most primal connection we have to the moon. The very beginnings of Western philosophy are also related to celestial events, lunar astronomy, and what we now call meteorology is weather, but at the time it was the study of space rocks and meteors, meteorology. And this is how people tried to understand our world, by looking outside of it for the first time and trying to make sense of that too. So the first person who really understands what the moon is, at least whose works survive in some form today, is this guy, Anaxagoras, who, and I might be saying that wrong, I don't know enough Greek I might be pronouncing it wrong, but he witnesses a solar eclipse in Athens, where he is a refugee from Persia, and he goes around asking people where they saw it from. He pieces together this story that helps him understand that it wasn't everywhere. The eclipse that he saw on the Peloponnese wasn't visible in Turkey, depending on where you are, which we now know is how eclipses work. But at the time, nobody understood this. And a total eclipse of the sun was an omen. It was a terrible event. It's a horrifying thing to behold or a very awesome thing to behold, but it meant something important. It wasn't just the movement of bodies. And arguably, Anaxagoras is the first to see it that way and to understand that it's a thing and it's somewhere far away between us and the sun, and that it's a rock, and that it may be earthy, and it has these features that are like Earth. And he puts this together after the eclipse and after the fall of a meteorite, which is the story of this meteorite fall is told throughout antiquity by various historians. And he is like, oh, this thing came from up there and it's a rock, and this is a rock, and so it's rocky, just like where I am. And so rocks are up there too, and kind of puts this together for the first time. And the problem for him is that this is heresy. And so he's put on trial and has to flee Athens. And his works are lost to history, but known to people like Socrates, who goes on trial for a similar heresy, and at one point is even blamed for Anaxagoras' ideas. And if you want to hear more about that, you can read Plato's Apology. But this is, I think, an interesting point in time for a lot of reasons, but because in classical antiquity, people for the first time start trying to make sense of the universe. And that concept really originates for the first time in this era. And the moon is one of the primary reasons why people start wondering about it in a physical way and trying to understand it and trying to make sense of why it's there in this period. One of my favorite works from this time is from Plutarch, who's a Roman statesman and historian. He wrote a bunch of biographies of Greek and Roman statesmen, but he also was a philosopher, and he wrote this treatise called on the apparent orb in the face of the moon, which is just abbreviated to de facie, which is the face. And it's this whole, like, typical for its time dialogue among a few friends walking the streets of Rome, talking about what is that thing, and like, why is it there, and like, why do we die, where do we go? It's this actually very deep and funny and thoughtful treatise that's really original especially in classical antiquity. And it's all based around these questions about the moon and why it exists. What is it doing for us? Why are we here? What is the point? All these questions start emerging in a literate way in this point in time, at least as far as we know, that in records that survive to today. And the moon is the sort of starring role. So at that point, after we have started to make sense of what the moon is and consider it and wonder about it, we start sort of changing the way we see the universe. And this is how we kind of transform the moon in both ways that are literal and more philosophical. We make the moon in our own image. After we invent philosophy and history and the study of history, we start inventing the science. And the story in the book really is more linear between the Mesopotamian cultures, who were very religious, to the first sort of scientific method. Because the first astronomers, the first scientists on Earth, were these sky priests who were tracking things like eclipses and the motions of the planets for astrology, for augury, to be able to predict events, for omens. But they were super accurate and super thoughtful about what they were tracking, and they left this huge compendium of data, essentially, that is used by later scientists and astronomers, especially Ptolemy and others, Hipparchus, to make catalogs of what is happening in the skies and to try to understand it for the first time. So I think there's actually a direct link between the earliest religions and the origins of the earliest religions, at least as far as the Abrahamic religions, and the origins of what we would consider modern science, the scientific method of empiricism, taking data, trying to interpret that data, and trying to understand the big picture. I think it actually originates with the religious priests of the Neo-Babylonian period. And then we get to these dudes. This is Galileo, Kepler, and in the middle, a guy that you might not know much about, Thomas Harriot, who is a friend of Kepler and a contemporary of both of these guys, but is an English mathematician who was I think, personal physician to Sir Walter Raleigh. This is sort of in the golden age of the Elizabethan era of science and astronomy. He is actually the first person to observe the moon through a telescope. It's not him. It's not Galileo. Harriot did it a few months earlier, and he knew about Galileo, and Galileo knew about him. But Galileo published first, and as all scientists know, publishing first is very important. Also, Galileo was trained as a painter, so he was an artist, and he was much better at rendering what he saw through a telescope. Harriot was not very good at drawing a picture of the moon based on like squinting through a little glass and trying to draw it. His were really not well done, so he never got any credit for being the first person to observe the moon through a telescope. I got to go see his drawings, which are in the collections of one of the aristocratic lords of England, the Earl of Northumberland. Has this in his personal collection. And so I got to go visit these drawings, which are really interesting in a way that I think, is important to connect the dots. Like we were starting to understand how to observe beyond the Earth for the first time. And we were starting to understand how doing that wasn't just this sort of passing fancy. It wasn't a thing we do, like I do, like many of you do, because it's just enjoyable. It was that, but it was also about trying to reach a higher level of understanding. I think of when I'm thinking about looking through my telescope or my binoculars, it's not because I'm trying to like prove something. It's more meditative than that for me. And if you read the writings of Galileo and Kepler and Harriot and their contemporaries, and Bacon and people like that, and even Newton, I think a lot of them were very meditative about it. They were very philosophical about what they were doing. But it really was this sea change where people were, for the first time, observing things about the heavens that questioned what we were told about them. And the things, as you all know, the story of Galileo, observing these things, and Kepler understanding them and sort of proving the Copernican model of the universe, really upends history. And I think it's because of the pure curiosity of these guys. Writing this book, it was like, I had to write a book about the moon that's going to include like Kepler and, Galileo and Apollo and all that stuff. Part of me was just like, this is well-trodden ground. Like, no one needs to know the story of how Galileo looked at the moon, and drew a picture and put it in Starry Messenger, and Kepler was, oh my God, but it really is so compelling, and they're actually great writers, and they're so thoughtful, and they're so moved by what they're doing, what they're seeing, that I just still find it among the most interesting stories ever told. And it's not a very far leap from these guys to the beginning of science fiction. So Kepler himself, I think, and argue in this book, is the originator of what we'd consider science fiction through the moon. He's kind of obsessed with the moon, and throughout his whole career uses it to try to understand and prove the Copernican system, which he believes in from the time he's in undergrad. He writes this long, actually it's not long, but it lived through most of his life. He worked on it time and again throughout most of his career. This short story called The Dream, and we just now call it Somnium. And it's really a satire in certain ways, where it imagines that he is this person that has a dream. In the dream, he's visited by these aliens from the moon who would then bring him to the moon and expound on how everyone on the moon believes that the Earth revolves around them. And obviously it does, because like, look, it goes over there and then it comes back over here and it goes around us. And so that's of course what it is. And the reader is meant to be like, oh, you silly, lunarians, you don't know anything, because that's not how it works. And it's a very thinly veiled critique of the Ptolemaic system and a sort of defense of Copernicanism. But it's also this kind of dreamland and like a fever dream about what the moon might be like, and like who might live there, and what it might look like, and what it might feel like to be there. And to get there, he imagines being able to travel out of the atmosphere. He's way ahead of his time, Kepler. And this book becomes kind of the first version that survives of humans wondering what it would be like to travel to the moon and why we would go and what we would do there and what we might find and learn about ourselves. And that sort of helps this entire flourishing of the, 18th, 19th century science fiction up to now, which many of you may be fans, as I am, of, more hard science fiction, modern science fiction, or Jules Verne, Washington Irving. Some of these are the most beloved science fiction writers of all time, end up using the moon again as a canvas for these stories, which are fun and entertaining, but also, I think, really instructive and really important ways that we can use to ask questions about ourselves. The moon is almost a safer way to address the problems that we have on Earth. Imagining going to Mars and living there, or living in the rings of Saturn, or even watch The Expanse, modern show and series of books about that. It's like an interesting way of trying to talk about our real problems in a way that feels maybe a little safer because it's a little further removed. And that's what I think a lot of good science fiction still does. The moon is the first place that we go to do that. And then, a guy named Werner von Braun and Konstantin Solyovsky read these books and become really inspired to do the things that are done in From the Earth to the Moon and Around the Moon, the Jules Verne lunar novels. And that's how we got there. And you all know the story of Apollo, so I'm not going to retread that overly. But that brings us to the future. And, what do we owe the moon? If the moon has been a primary cause, or at least a primary player in all of these human enterprises, from literally the evolution of backbone creatures to the origins of modern philosophy, are we just going to go and strip mine it now? And who gets to say, and how are we going to divide it up, and who's in control? And I don't claim to have the answers, but I do think that we need to talk about that. And I don't think anyone's talking about it right now. So that is the sort of upshot of this entire book, is where do we go from here? I hope that we can at least start talking about that. I think that's all I've got. Oh, and then, so this is, again, my slide. I think an instructive model for what we might want to do is Antarctica. It's a place that is austere. It is really hard to get there. It's expensive. You need a lot of special equipment and training, and you don't want to be there very long. There's interesting stuff to see and to do. We can learn a lot about ourselves and our planet by going, but no one gets to lay claim. We've all decided as a world, most countries have signed the Antarctic Treaty. And even if we haven't signed it, there are sort of mutual agreements for cooperation and, limiting extraction in Antarctica that I think could be very instructive for our use of the moon. There's a lot of science happening down there. There's a lot of people living down there, coming and going. And we can do that on the moon as well. But I think it's special, like Antarctica is special. It's a part of Earth, quite literally, physically, a part of this planet. And it's a part of every culture. It's the only thing every human who's ever had sight has seen. Not everyone who's ever lived has seen the ocean or a mountain or a thunderstorm, but everybody on this planet who's ever walked on this planet has seen the moon. And I think that, again, is a really important thing to keep in mind when we head back up there. So I think I will leave it at that. I don't know how much time we have, but that's kind of the gist of my talk. So I'm going to stop sharing my screen.
Okay, thank you very much. All right, well, there's been a lot of talk about how the Earth needs an advocate. Rebecca, I'm voting for you for the moon's advocate. So, any questions? Okay.
Do we have any questions on Zoom?
Someone pointed out that, the full moon in June was about as low as it could get on the meridian, which is, that's exactly right. That was most extreme low point back in June during the full moon. And somebody must have noticed that. It was very clear to me. I live on the side of a mountain and I have the view to the south and the east. And it was like right in my window, very bright. And right now it's like I can't even really see it in my house. I have to go outside because it's so directly overhead and as part of this lunar standstill 18-year cycle. And I didn't talk about Chimney Rock, but there's a few places on Earth where people figured this out, that the moon would do these very extreme paths through the sky where, at this point in the major lunar standstill, it's rising and setting at really extremely different locations throughout even a single cycle, let alone the whole calendar year. And people on every continent noticed this and started to pay attention to it. And in many cases, erected monuments to it and megaliths and landmarks that were used to track this event, or at least to be used to commemorate it every 18 years. And some of these are in northeastern Scotland. Some of them are in the Midwest of this country, in Georgia and Ohio. There are a couple earthen landmarks, earth mounds and things like that. And in Colorado, there's one that's actually a natural formation of sandstone that was carved by a river in southwestern Colorado. And the ancestral Puebloans, who were also called the Anasazi, created a great house there in a village about 1,000 years ago. And at some point they left and moved on. And this is the same people who lived in Chaco Canyon and Mesa Verde and kind of other places in the Southwest. But they noticed that every 18 years, the full moon rises through in January, rises directly through these spires, these sandstone spires. It's really stunning. And this was an important enough thing to them that they built an entire village at the base of these two sandstone spires to be able to see this and to track this event. And same with Tom Naveri and other stone circles in the book. And I think about that sometimes in terms of like, this is before people had written language or math or any kind of system of record keeping that survives to now. They had petroglyphs and things like that we can kind of look at, but this is a very sophisticated method of sky watching, and it must have mattered. Like, why would you remember 18 years to do the same thing, to look at the moon in this location? That is a long span of time, especially for people whose lifespan was maybe 40 years at the time. So it must have had really deep meaning to these people. And then, I mean, people here 1,000 years ago, people in Scotland 10,000 years ago, people in Indonesia, noticed the same thing. And I like thinking about why and why it mattered to them and what they must have done with that information.
All right, well, thank you. One question, yes?
I'm just wondering, what was the most surprising, I'll say, fact that you learned about the moon in researching this book?
Oh man, I don't know. There's so many that are like, I think that one of my favorite things I didn't know is the guy who predicted and then was later proven correct the theory of plate tectonics is this German scientist named Alfred Wegener, who was laughed out of the room when he invented this theory in the 1920s. And he came up with this idea because there was this big debate at the time around the moon's formation. So the most popular theory, which I never knew this until writing this book, was that the moon was calved from Earth, like the way like a glacier, calves an iceberg. And this was a theory proposed by George Darwin, son of Charles, who figured out some algebra and was like, well, this is the way where the moon is now is distance from us, and this angular momentum and all these different things to kind of arrive at this conclusion that in the very distant past, it was right there, which is true. And he figured, well, then that's why the Pacific Ocean is so deep. And that's why the continents look like puzzle pieces, and you can just shove South America up there under the shoulder of Africa and it fits neatly. And that's because something happened and the moon got ripped off of Earth. And this was sort of the common theory at the time in like the late 19th century. And Wegener was one of the people who was like, I don't know if that's right. Like that seems kind of weird to me. And he proposed this theory of seafloor spreading, which is true. And it took until World War II sonar to prove that he was right. And I never knew any of that until writing this book.
Okay, we have one question here. Go ahead. Right, okay. I'll repeat the question. You were talking before about how minerals on the Earth, rocks on the Earth, and the moon are virtually identical isotopically, right? Even though physically they may be different. Can you
Sure,
just
yes.
expand on that a little bit?
Oh, yeah. Well, the isotopic difference is really hard to distinguish because the ratio of things like the atoms of tungsten relative to the atoms of hafnium, are really similar. And usually those are things you can use to distinguish items from one another, from a Martian rock versus an Earth rock, or the ages of rocks is an important way we do that. Just on Earth, comparing the ages of Earth rocks, like when this rock formed versus this rock, you can use different argon, tungsten, hafnium, or like versions of elements and their decay that you can use to figure out a rock's identity, essentially. But yeah, they look nothing like Earth rocks. And I got to go see some of the moon rocks in the Lunar Sample Lab at Johnson Space Center. And that's still among the most absurd things I've ever done and seen in my life. The chapter on Apollo really is about that pilgrimage to the moon rocks, because they are so obviously not from around here. They look nothing like any Earth rocks. Earth rocks are all kind of tired and, soft and molded by rain and wind and time and waves and all these processes that we are so familiar with on Earth. And so they all look kind of weary, or like weathered. I'm holding a piece of Connemara marble from Ireland. It's sort of like soft and it looks like it's been beaten down, because it was. And the moon rocks are like jagged and crystals and like blocks, like you were, slabs, like you're cutting them, because they did cut them. It looks like they're from a quarry. And if you walked into a room and someone said, like, which one is a moon rock, it would be immediately obvious to you. If you looked at them under a microscope or through a chemical analysis, you would not be so sure. But physically, they look very different.
But how are they the same?
They are the same chemically. So like the isotope ratios of various elements are the same in Earth rocks and moon rocks, which is unexpected. Like we would expect them to have different ratios of things like oxygen, like very volatile elements. Because of the way that we think planets form, they coalesce from, puffballs of dust and gas around young stars, eventually sort of clump together in a process we still don't really understand very well. And then they get large enough, they start to self-gravitate and eventually differentiate. And, the metals in them separate, and then you can and you see there's a core, and there's Earth at least has a, dense core and a mantle and then an outer crust, and Mars is similar, Venus is similar. And the ways in which these things happen is related to their place around the sun at the time that it happens. And so it's like an accent. This is how I've tried to describe isotope ratios in planetary science. It's like by looking at the numbers, the just numerical values of the isotopes that you're counting, the ratio of these isotopes. Sometimes it's argon to argon, sometimes it's hafnium, tungsten. Those are the most common ones in lunar rocks. The ratio gives away its place of origin. Like somebody from New York, you can tell, like they have this accent from the earliest age. They're imprinted with this, and the rocks are imprinted that way. And so if the moon is the remnant of the impactor from the giant impact, then it would look like that thing. It would have whatever isotope ratios that object had, which would be different from whatever Mars had and whatever Earth had by virtue of planetary formation, like just because of where they are around the sun, the temperatures and the critical point of various elements and where they condense at certain temperatures and pressures based on the age of the sun. Like you can kind of do a lot of chemistry to figure these things out. And this is a tool in planetary science that people have done for a long time and measure these different ratios of isotopes to tell which is which. But you can't do that for moon rocks and Earth rocks because they look the same chemically, which is very strange. And that's true of like a dozen different elements that we've looked at. It's various ones. It would be one thing if it was an outlier. It's like, oh, well, all the oxygen is the same, but like that's oxygen's oxygen. It's kind of messed up anyway, but it's not. It's various ones that are all very different in terms of their chemical properties to each other. But if you compare the Earth isotope ratios to the moon isotope ratios, they're virtually identical.
Okay, well, thank you. In the interest of sort of moving along, thank you very much. I'm gonna, let's conclude.
Victor, I hope you're going to send a AAAP hat.
We'll take a break and then we have Rex and Bob who have a few things to tell us. So thank you very much. Look in your mail. There's a hat on its way to you.
I appreciate it.
All right, take
All
care.
right.
Good night, Rebecca.
Thanks a lot.
Okay.
Thanks for having me.
All right, you're up, Rex.
Great. Hey, hello, everybody. Yes, so that was a fantastic discussion by Rebecca Boyle. I absolutely love that. So thank you, Victor, for putting that excellent talk together, and getting her to come in on the Zoom was wonderful. We have a few things we're going to do tonight. We're going to try to go through some really interesting stuff and still get out by about 10, so bear with us. The first thing would be the Unjournal Club, and we'll launch that in just a minute. This actually comes in from an idea that was pitched by Rich Sherman. Rich, I hope you're still on because you instigated this. And so we're going to talk about some new ideas about dark energy, and I'll try to do a quick intro, introduce why there are new ideas, and then Bob really is going to take it to a new dimension with some of his own ideas. And then we'll try to save some time after the Unjournal Club to get into some other things going on in the AAAP. Astro images from members, you're welcome to share them. Anybody on the Zoom can share them by sharing screen, or if you are in Peyton Hall, give Bob a thumb drive. I know there might be some opportunities there, including last night's Mars occultation event. And I was going to mention, and we don't really have to look at my chart, but you can see in sidereal times, I put in a chart something you're all aware of, but it's an unusual occurrence of all 7 of the planets can be visible in the sky later this month, basically within a week. If you start at sunset and are willing to stay up all night until sunrise, you could see all 7 of them. Mercury, though, is so close to the sun, it's a pre-sunrise object, but the other 6 are all visible at the same time early in the evening, like 8 p.m., which is kind of a very unusual occurrence. And too bad it's the bitter cold of January, because maybe we could have an observatory event. I don't know. I'll leave that for Dave. Probably not worth going out to the observatory for, but some really cool sightings. And then I'd like to chat, if we have time, about any things going on with outreach, including I'd like to propose that members start thinking about field trip propositions for later in the year, not for the winter, but more like spring and summer. I don't know if we'll have time to talk about this, but I've had this on the agenda a couple of times, and we've sort of haven't got to it. But this club used to be very active in doing physical field trips and trying to experience astronomy. Probably, I'm thinking of small groups, not like 50 of us, but more like 10 of us going down to the DC, for example. And I've had it on my list for a long time to get to the Udvar Hazy Center for flight and what am I trying to say? Aerospace stuff. So anyway, last comment I want to make is that I'm tossing this out there to board members and other committee chairs that we probably need to have a board meeting, and I'm proposing February 4. So get back to me about whether the night of February 4 would work for a board meeting. We have not had one for quite some time, and there's some important things to discuss. Okay, so enough of that. I'm going to try to bring it on now. Last month, I was talking to you about sort of reconnecting to our September talk by Dr. Bacall from Princeton, and the amazing story behind the understanding of dark matter. And she alluded to the concepts that are out there that have now congealed around the idea of dark energy. dark energy is a very mysterious thing. And as we talk about it over the next 10, 15 minutes, I'm just showing this slide because it comes back to Vera Rubin, who was really the person who woke up the astronomy community a couple of decades ago to come up with the really solid evidence that proved the existence of dark matter. And this fantastic observatory that's supposed to come online this summer down in the Atacama in Chile, the Vera C. Rubin Observatory, originally called the LSST, with an incredible high technology, new design telescope, 3-mirror system, and the largest camera ever designed for a telescope, 32 gigapixel camera is going to begin, we'll get first light this summer if all goes well. And the point of this, well, there are many scientific goals, but one will be to try to get at really being able to verify the existence of dark energy. And it all has to do with supernova and other types of information based on the evolution or the history of the universe. And you've all seen this slide. I stole it from somewhere on the internet, but a number of people have published slides like this. And the idea is that dark energy, the concept of dark energy really only became evident later in the universe, out around 10 billion years on the right side. Dark energy evidence rests upon seeing evidence of the expansion of the universe accelerating. So the very expansion itself is accelerating, an increase in the rate of the expansion of the universe. And as you go back in time, that increase in the rate of expansion goes faster and faster to mind-blowing levels. And they talk about it in terms of like hundreds of kilometers per second per cubic parsec, if you can get your mind around that unit. And I cannot. But the reason I'm bringing this up is, as I said, we wanted to have a talk about it. And we don't want to talk now about the standard model. The standard model is that cold, dark matter, and the requirement for the lambda constant addition to the equations, which accommodates the need for some form of energy that we cannot understand to be providing the kick, if you will, for that expansion of the universe. And it's been largely based on supernova observations, the redshift that you see with supernova, which can be calibrated as sort of the standard candle of the universe, and things don't fit. And this is where the idea has come in. It's observational evidence trying to support what is the exact, let's say, the quantification of this so-called dark energy that cannot be ascribed to any other physical foundation that we have in physics. So that's all well and good, although difficult to understand. But even more recently, a group, actually this is the paper that I'm showing you, by a group led by David Wiltshire, and these guys are down in New Zealand, have been publishing, and he's been the champion of an idea that the cosmological model is wrong. And he's coming up, he and others that are sort of in agreement with him, that a more careful analysis of the supernova spectroscopic data set suggests that the standard homogeneous cosmological model, that is spatially flat, cold dark matter, the so-called lambda CDM that Neda Bakal was telling us about, is not correct. And he's suggesting something called the timescape cosmology. That's like a cute term that has been bantered around. But what it really means is that timescape replaces dark energy, and even the need for dark energy to even be hypothesized, by something else, a kinetic gravitational energy. And gradients in kinetic gravitational energy can explain the cosmological observations and the redshift of the supernova. What he's saying is that the data, in a more careful analysis with something called Pantheon, which is a big data analysis of all the existing data on type 1 supernova and their redshifts, he's saying that basically timescape is a better fit on the data. And timescape really means the clumping of matter leading to the idea the observed accelerated expansion of the universe is an illusion caused by the uneven distribution of matter, and that time runs at different speeds in different regions of space with different densities of matter. It's not homogeneous, it's unhomogeneous. And particularly in the vastness of the cosmic voids, he's saying that the timescape model eliminates the need for dark energy to even exist. That it basically it's a misinterpretation of the data. So this is one of the latest things saying that the universe's apparent accelerated expansion is a result of the relativistic effects of inhomogeneities, clumpiness, if you will, at a very, very large scale of space. And so he's talking about gravitational time dilation being the real explanation for the expansion and the acceleration of the expansion of the universe, and that the interpretation of dark energy is basically wrong. And that's sort of where I'm going to leave it here, because I think we are at a stage of the evolution of cosmology where things are changing and new types of data and better data and more of it coming in from this new telescope, the Vera Rubin Observatory, is really going to change things. And this thing may get settled out. And we are living right in the midst of it. We're living right in the midst of the controversies and the changes of a major theorem. And I'm saying that it looks to me like, and I'm not capable of understanding all this, but it looks to me like dark energy may well fall and that it won't stand these new tests of data. And now that leads me to hand it over to Bob. And Bob has thought about this a lot more than I have and can probably explain it more coherently, but yet a different way of looking at the problem. And Bob, maybe you take the helm here.
Okay, I'll take the helm. Yeah, so I have really nothing to say pro or con to what Rex just described, because I'm not a cosmologist, but I just wanted to spend a few minutes mentioning something that puzzled me for 20 some years, ever since I first heard about dark energy. And I thought I would mention it to you because I do think it's kind of fun and interesting. And it doesn't start out about dark energy or dark matter. It starts out just about physics a little bit. The existence of our universe. It's matter. What's that matter? There's no antimatter. Of course, physicists in laboratories have made antimatter from nuclear reactions. And so we know that there's matter called proton, there's an antiproton, there's neutrons, there's antineutron, there's anti for everything. But yet those anti things don't really exist out in our universe, in any measurable quantity. And I have to say, ever since I first learned about that, I found that to be weird. This universe was created. There's these two kinds of things, and we're only one thing. I find it weird, and so I have a conjecture, which I like my conjecture, but I've told my conjecture to pretty much everybody in Peyton Hall here. No, I'm kidding, but to lots of people in Peyton Hall and astrophysicists in general, and all of them tell me that what I'm going to tell you now is just ridiculous. But I like it, so I wanted to spend a few minutes telling it to you, because maybe 100 years from now, maybe it'll turn out that I'm not ridiculous. And so here's my conjecture. Maybe antimatter is gravitationally repulsive to matter. And so there wouldn't be an antimatter moon around Earth because it would push away. And so maybe after the Big Bang, half of the universe was matter and half of the universe was antimatter. And maybe that's still true. Maybe that galaxy over there, maybe that one's all antimatter. And maybe that one over there is all matter. Now, of course, we see galaxies colliding. Now, if these are gravitationally repulsive, an antimatter galaxy wouldn't crash into a matter galaxy. They're pushing apart. And so if they did crash into each other, this would be a huge explosion, but that wouldn't happen. And so it's really, in my mind, possible that half the galaxies we see aren't made of matter. we don't go there. We can't tell you that they're matter or antimatter because the things in terms of the photons that we get would look exactly the same. And so I think that would be interesting if that's reality. And I think it's possible that that's reality. And if that is reality, that could explain dark energy. Of course, maybe as Rex said, maybe dark energy is not a thing. But if it turns out it is a thing, what I just suggested is a conjecture that could explain it. And I've mentioned this conjecture about a year ago to a fellow named Stu Smith, who's a physicist here at Princeton University. He used to be the dean of research here at Princeton. I've known him a little bit in his role as dean of research for many years. About a year ago, I went to a talk that he gave to the general public, not a technical talk about stuff he does, about particle physics. He talked about neutrons and protons and stuff in this talk to the general public. And afterwards, I asked him, I said exactly this conjecture to him, that maybe antimatter and matter are gravitationally repulsive. This is not an easy thing to measure because we don't have much antimatter here on Earth, because all it has to do, that antiparticle has to just hit one matter particle and boom, it's gone. It's just photons or energy, whatever you want to call it. And so are they gravitationally attractive or gravitationally repulsive? I actually looked this up 10 years ago, and there was an article that was published by some postdocs at Caltech, I think it was, just a few young researchers, and they had not the exact same hypothesis, but the same question. Is matter, antimatter, gravitationally attractive or repulsive? And they described an experiment they did at Caltech, and they had that it was gravitationally attractive, not repulsive. But their window of uncertainty spanned all the way to being repulsive. It leaned a little bit toward attractive side, but plus or minus, 2 sigma included the gravitational repulsive part. So it wasn't a definitive proof that my theory is wrong. But when I mentioned this to Stu Smith, and this is the one funny thing I wanted to mention, I mentioned this to Stu Smith a year ago. He's up here at Princeton, but he does lots of research with data and with people at CERN, which is this physics laboratory in, where is it, Switzerland? Where's CERN? Where? Switzerland. And literally the day I mentioned this to him, people at CERN released that they had just done this experiment to see if matter and antimatter attract or repel each other. And they got that they attract each other, which proves my theorem, my conjecture, let's not call it a theorem, my conjecture to be wrong. But, I still think maybe they'll discover that their experiment was wrong 30 years from now. Probably not, but maybe, because I still think it's really, really, really weird that our universe is just matter and not antimatter. I find that weird. I mean, maybe none of you find that weird, but I do. And so, oh, by the way, Stu Smith also told me that people weren't talking about galaxies being matter and galaxies being antimatter 100 years ago. But when antimatter was discovered 100 years ago, Stu Smith says, the scientists who discovered antimatter were wondering, is it gravitationally attractive or repulsive? But 100 years ago, they couldn't do an experiment precise enough. So he said that people were thinking about this from the very beginning, but they don't, in Stu Smith's point of view, they didn't really have an answer to it until literally the day I discussed it with him a year ago. So anyway, that's all I wanted to say about my view of dark energy. And I'm probably wrong, but I might be right. Low probability, but maybe. So anyway, that's what I wanted to say. I'm done with that. I guess unless there's questions for either me or Rex, we can be done with the journal part. And yeah.
It's just announced that the latest simulation models of the Big Bang actually produce another parallel universe.
which is all antimatter?
Would be, as you said, suggest. Can't hear it on Zoom, sorry.
Oh, just come up here and speak. He can't hear you.
Yeah, let's do that.
Yeah.
I was just saying that it was just announced that the latest simulation models of the Big Bang, where the older models just created our universe. Well, the latest ones now actually create two, and that the latest models. So Bob's conjecture that it could be possible that where all the antimatter actually resides is actually in the other parallel universe, and that there's people like us who are made of antimatter are having the same discussion about why there's no positive matter in their universe, right?
So why are they apart?
Well,
the question.
that creates another simulation model, right?
Yeah,
But
yeah.
yeah.
Yeah, so that's it for the end journal parts. Is it time to switch over to the business meeting? Rex, are you gonna take over for the business meeting?
Yeah, sure. Let me just go ahead and pick up the thread by sharing my slides again. Yeah, where was I here? So, whoops, sorry about the flashing. So, yeah, so I would just leave that as stay tuned to really what's emerging, because it's we're in a great period of time in cosmology where the types of theories that we've been hearing will begin to have much more solid experimental results that can be used to correct the theory if they need to be corrected, like the Rubin telescope. I mean, this is going to be a major. There's never been anything like this with the amount of data and the depth to which they can get the data. So things are going to be happening, and we get to live through it. So yeah, so a bunch of us were on a Zoom last night trying to watch the Mars occultation with the moon, and that's such a cool thing to see. I mean, I need the principals to speak up for their work, but I'm just showing you some things that were captured and sent on the Astro Imaging group last night. This is an amazing one here. This is by, this is Bob?
No. That
Speak
one.
up.
That might be,
Is yours, Dan? Is Dan on the meeting? Dan Mintz? Some really cool images here.
Wow.
This is an amazing one here. Look at this.
no, right on the edge. Yeah.
Yeah, that's what we were looking at last night. Okay, so there you go. Look at that.
Oh, wow.
Well, I'm sorry to flash through those so quickly like that, but I mean, if you're interested in the stuff, get on astroimagers.io, the astro photography group that we have in the club. Oh, awesome. Oh,
That's awesome.
it was great.
Truly.
It's amazing how the
Little time acceleration there on the backside.
I
Very
love
cool.
the music.
Chugging along.
Oh, it's just here. There we go. See it?
Yes.
Right. So I had the opportunity to when Jupiter was at opposition, the exact night, that evening it was at opposition. It was in opposition. I set up my 140 ED doublet, and on the one part of my yard that faces south, that's open through the trees. And it was about 11:55, just a little before midnight. And I used my ASI 585, and I had a power mate. This was the same setup that I got the image of Jupiter earlier in the year of, last year. And used the same setup. So I had the image scale was about 0.24 per pixel. That's about f17.5. I used ASI capture, and I set it up to capture 5,000 frames at a gain of 300, and the exposure was 11 milliseconds. So I followed that theory of just short exposure and, just grab frames and high gain. I get that. That's the idea, right? Like short exposures, high frame. And what I forgot to do was to shrink down the region of interest. So it's a little bigger. It's 1928 by 1080. But the interesting thing, and I didn't even plan for this, I just knew it was at opposition, is that if you can look closely, you can see Io, and there's a shadow transit going on. And the shadow transit, the shadow itself is right next door, or right next adjacent to a storm, a newly appeared storm that was in the southern equatorial belt. And it was just all like, there it is, and I grabbed it. So it's pretty neat.
Nice.
That's great, sharp detail. That was great.
Yeah, that's awesome.
And I used the ASI, I can't think of the name of the little utility. It's their video stacker. So I didn't, there's no processing in this or anything else. This is just
built in.
Yeah, this was built in, the one that's built into the ZW ASI, ASI Studio. And you just drag the file on it, and boom, away it goes. And it still amazes me that when you're watching it, recording it, it's just a ball of mush dancing all around the screen. How are you ever going to get anything out of that? And then you just take the file and drop it on there, and about 2-3 minutes later, boom.
Yeah.
The one thing I'm gonna when I do this again, because I know Jupiter has a very high rotation speed. So what I was thinking, I know there's a ballpark number that if your exposures are under X amount of minutes, that it minimizes that.
Right.
Is there a value for that?
You mean to minimize the distortions?
No, not the distortion, but the rotation latency. So I
Right,
know,
because that's going to blur the details if you go too far. That's right.
yeah. Does anybody know what that number is? I'll have to look it up, because
Not
next
off the top of my head, but Tom, we should play around with your data with auto stacker and registack sometime and do the wavelet filters, because you can sharpen it. This is a great image, and you can take it even further.
Yeah.
Send us the AVI file.
I think I still have the raw files too.
Yeah.
Because it might
All
even,
you need is the video file.
I probably have the raw video file. I think I still have it. So
It's an AVI.
I'll send it to you guys. You can play with it all you want.
Cool. It's really cool.
I have a question
Hey,
for you.
Tom,
Yes.
ASI video stack.
Yeah.
So you took a video in ASI cap
Right.
and then dragged it into ASI video stack.
Exactly. You just drop it on there. You tell it how many frames you want to use, the percentage, and hit go.
Wow.
Yeah, it's great.
So this is the second planetary image, and I know Rex, you had put up the planetary challenge that time, so that's why I had the opportunity. I figured I'd give it a shot, and I would have brought this up at the December meeting, but I was recovering from COVID and not in a very social, jovial mood, you might say.
I think if anybody's interested, we have that presentation that I did, and there was a bunch of discussion with the guys on how to do planetary processing. It's in the YouTube channel with one of the astrophotography group meetings from last winter, I think, last January, maybe it was. Great job, Thomas. Beautiful.
Yeah, it's still surprised the living heck out of me that you ran the thing and
Just
like,
going
wow,
directly into rehab.
What Jen say?
Hey, Jen, you need to mute.
Yeah, I am. Sorry, I didn't realize.
Well, hey Rex, I have a lucky image rather than a good image, if you want to see it.
Yeah.
Yeah, bring it on. I think Bob may have to stop sharing that.
Oh, stop the share.
Yeah.
Sorry.
You know,
See if I can do this.
you can inject my drive.
Go ahead,
Um,
Rich.
All right. Can you see it?
Yeah.
Yeah.
So I just decided to do a solar at one point, and last week or so, week and a half ago, and lo and behold, I guess it's a Piper Cub or some kind of aircraft kind of
Oh my
flying across,
gosh.
which
Look
has
at
turned
that.
out
That's
kind of
Oh,
amazing.
wow.
I think it's a drone.
Wow, the timing.
Oh, that's
Well,
great.
I mean, I wish I could have pressed the button faster because it would be a little further left, but I was so excited by it. I was like, what am I going to do? I was like, just press the button. You're a photographer, for God's sakes. So I just pressed the button.
Oh, that's great. Wow.
Yes.
I think it's a Cessna 172. I was going to say that's the weirdest shaped sunspot I've ever seen.
There you go.
That was my comment.
Yeah,
I'll give it back to you guys.
that's truly lucky imaging.
Story of my life.
Timing is everything.
Yeah.
All right.
Those were a lot of sunspots. What day did you take the image?
What day was
Hang
it?
on, Jen. Hang on, Jen. Let me
Okay.
let me take a look. Give me a second.
Sure.
You guys keep going. I'll
Okay. Anybody else want to show anything? Should I show the fake video that I made?
Yeah.
All right, here's a fake video.
Bob has a big story about his endeavors this night.
Oh.
It involves dark energy.
It involves no energy. Zoom, share screen, full screen, share. Go over here. You see it?
Yeah.
Yep.
Okay. This is a video that I made, but it's not the video that actually happens like you're seeing it here, because I screwed up. I was watching the occultation on my computer, this computer right here, which was attached to my camera on my telescope, seeing it live and recording it as a video. But for reasons that I don't want to go into, I didn't. The acquisition got terminated before the event, and so I didn't actually get a beautiful recorded video, but I was watching it, and I did see it, and it looked like this. So I took the moon from that I got in my video, and I took Mars as I got it in my video, and just today I made this fake video showing how it, but this really is how it looked. So, but it's fake.
Love it.
Come on, Bob, you got to share why, because it might help somebody in the future.
Oh God, okay.
2 words.
Well, Mars is only like 15 arc seconds in diameter right now. It's like
Yeah.
a tough thing.
Yeah. No, the problem that I had was I was trying to capture the video in a different way than
I
people
don't know about
usually
you guys,
do.
but I've lost audio.
Oh, you can't hear me? Can you hear me? Rex? Rex can't hear me.
No, we're hearing you, Bob.
Is anybody else
Yeah, I
hearing
can hear
audio?
you.
Yeah, so I'm not a big fan of AVI files. And my new I don't have a Windows machine anymore. I used to always have a Windows window on my Mac machines for 20 some years. So I did all my Astro stuff using Windows operating system, which is where SkyStacker and all these things work. And I've used all those, but my new computer, this one that's sitting right here, doesn't allow there to be a Windows system on it. And so I've had to sort of adjust my things, and I don't have an app that will analyze AVI files on my Mac. And so I'm like, oh God, how am I going to do this? I don't want to use my old computer. I want to use my new computer. And so I had an idea just to use this thing called QuickTime Player. How many people know QuickTime Player? And in QuickTime Player, there's a thing called start a screen recording. So I figured, I'm just watching this on my screen. I'll just do a screen recording. And I practiced this for a couple hours last night before the actual event to make sure I knew how to do the screen recording. I practiced it and everything was working just fine. And then, but those videos were only maybe like 30 seconds because I was just practicing. And then it was time to do the real capture of both the ingress and then an hour later, the egress. It was going to be like I don't know, I was going to do like a 3 or 4 minute capture. And when I did the ingress, and I went to I got the ingress and I watched it. But in fact, my wife, Chris, came out to watch it on my computer, real live with me. Wow, that's so cool. Look at that's happening. And then when it was all done, waited maybe like a minute just to whatever. And then I went to turn off the capture and it wasn't capturing. And I had no idea why. And then an hour later, for the egress, the same thing happened. And I still had no idea why off the top of my head. But then because I was on a Zoom meeting with a bunch of you folks, we had this discussion and I think it was I who made the conjecture that, oh, while we were capturing the video, while we were watching this, my computer went into screensaver mode. And maybe that automatically turns off the record. And it was only for like 1 second because I was sitting at the computer when the screensaver went on. I just went like this, just wiggled my finger, and it came back. I didn't think that was any big deal, but that was the only conjecture I possibly could have as to what went wrong. And so we tested it last night, just as an experiment. Put the screensaver on. Oh, it stopped the recording. And so that did happen on both of those longer intervals of time because I was just kind of waiting for 2 or 3 minutes and I wasn't just wiggling my finger for the whole 2 or 3 minutes. Had I done that, I would have had beautiful videos to show you right now. But because I didn't go like this for 2 minutes, I don't have them. So I'm kind of depressed about that. But anyway, end of that story.
Thank you for sharing, Bob.
Well, just moving along then.
Okay, yeah, let's
if you
move
stop
along.
sharing.
Yeah, I got to figure out how to
If
stop
you
sharing.
stop sharing, then I got something to throw up there.
Hold on, let me go to the share. Here we go. Stop sharing.
Yeah, there you go.
Hey, Jen, that picture was on January 1st.
We're seeing your screen zoomed in. Yeah, okay, that's better.
Want me to turn the mic on mine?
Thank you.
So this is the star chart I put in Sidereal Times, but it's kind of an amazing lineup of the planets later this month. The ideal date would be around January 25, but really it's plus or minus a week. And you can see this is about 7 to 8 p.m., 7 p.m., I guess, in late January, with Saturn and Venus over in the west, Neptune, Uranus, Jupiter in great position, as we just saw from Tom's work, and then Mars, which you guys have been looking at. But it's an unusual configuration to have all 6 of these guys. And then if you get up early in the morning just before sunrise, I think it'd be almost impossible, but technically Mercury is in the sky. So that makes it the rare occurrence. Yeah. This is what it looks like from sort of a topocentric point of view.